Hey, what's up? Welcome to my channel. I'm Yuri, and it's me again. Today we're gonna build something from scratch, and today we're gonna build Malloc, realloc, free, and calloc from scratch in C. So let's head right in. Before coding, I just want to say I want to change the style a little bit because well, in the previous video, I was just sitting there and code the whole video, and I think it's pretty boring. So I think from this video we try to build build the tools using a tutorial on a website that maybe the viewer, you guys can follow along, and I will just follow the tutorial because I kind of get the idea of how Malloc work and everything else, and kind of have some idea about the virtual memory and kind of memory management, but just don't know how to build it. So yeah, we'll start to building it together, and hopefully you guys will enjoy this video, that maybe we can learn something from this video all together. So this is the guide, right? I will put the link below in the description so you guys can see. So we will just implement a simple Malloc. It's not a completely full working Malloc, just like C language using right now. It's just a simple one that we get the idea of how it's work, and it's like a toy version of it, And before heading to the video, if you guys don't know what it's Malloc, I'll kind of explain a little bit. So Malloc is a functions that allow us to borrow memory in C. So I'll show you. So let's go here. Let's say Malloc. Let's go to descriptions. So Malloc is the functions allocate bytes and whatever. So we just it's gonna return something. Then Malloc return a unique pointer to the value that can later be accessed. Basically, Malloc gonna return the pointer to the memory that we borrow from the operating systems. That's it. And yeah, we're gonna implement free callocs and everything related reallocs all in this video. So stay tuned. Alright, so let's start. Let's make sure I have a draft here. This is on plain, so I can draw something for y'all. Okay, so you can hide this. Alright, perfect. Alright, we already know what is this Malloc. Alright. Oh, and just kind of have the idea of how we're gonna implement this. So as you guys know, Malloc is not a system call. Despite is give us the things from the system, which is memory, but it is indeed not the system call itself. But Malloc is like an overlay. It's like it used some system call within it, so it's like kind of an allocator, an orchestrator that use all of the system call like BRK, SBRK, or a map that we're gonna go later on in this video. So it's gonna smartly integrate these and handle everything for us. So that's why Malloc is really convenient to use. Even though we can use this directly to do system call to get memory, but Malloc is it's a fucking magic, bro. If you use Malloc, you know, right? We use Malloc, and then we just free what we use is so convenient. Well, let's say for example, if you initialize like 10 pointer or 1,000 of pointer, and then for each pointer you use a malloc to borrow a bit of memory from it, and then you just can free it when you want. So have you ever imagined that, like how it's work, like how everything work under the hood? Well, we're gonna go over it in this video. Okay, so malloc get memory from the heap. Normally, if we initialize or we use a variable, whatever, in our program, mostly the data gonna be stored in the stack memory of the RAM. That is gonna be destroyed after a program ends or out of the scope of that variable. But for heap, it's gonna stay still and live in the memory. It's live in the heap. So this is the heap is a region in our RAM that is can shrink, this can expand, really convenient. So this has right in. I'll kind of read this a little bit so you can see. Also, let me just zoom this out. Yeah. So yeah, just keep in mind that malloc, it's just an overlay that within malloc, it's a function that we use a bunch of system call to get memory. That's it. So we need to understand how memory is managed in most multitask system. We will keep an abstract point of view for that part. See many details are system in our whatever. Okay, so this is the heap that we're gonna use here. The heap gonna have, just keep in mind, this is pretty important. The breakpoint, it is the process break. That is the locations of where the heap ends. That's it. So this point, which is a memory address, that it's just gonna indicate where the heap ends. Yo, what's good, bro? So here the author state that in order to code a malloc, we need to know where the heap begins and the break positions, right? And of course we need to be able to move the break later on when we that is how we shrink and expand our heap. That is a dynamic, it's a dynamic regions, memory regions that we're gonna use by we're gonna expand and shrink it by changing our break locations, right? And how we're gonna change it is by using BRK and SBRK. Okay, so here is the description of what BRK do. Let me just read it. BRK plays break at the given address and return 0 if successful, and something like that. And SBRK, we move the break by the given increments in bytes. So in summary, BRK, we pass in address pointer as an argument, and it's gonna move the breakpoint directly to that specific location. But for this SBRK, what we're gonna do is that we're gonna pass in the bytes as the argument. It can be either positive or negative, so it can shrink or expand the SBRK, which is the break, process break. So for example, if the SBRK is 0, it's pointing, let me try it. So if this is when we start the program, this is where our SBRK is currently pointing to. So let's imagine this is the heap, right? This is the end of the heap. It's just kind of small like this because when our program starts, there's nothing in our heap, right? So if we say SBRK of 4096, it's gonna expand our heap by this amount of bytes. So now it's gonna be expand like this, and the SBRK gonna move to this. If we do SBRK 0, it's gonna return the current and, which is also mean it's gonna return the process break address. So just keep in mind this. Let's go here. In map regions. Oh yeah, we also have, it is pretty important too. When we are borrowing the memory from our kernel, so this is the the big code regions. Just imagine that when we are calling malloc, for example, if you are calling malloc of 1,000, well, it is not directly giving you just 1,000 bytes, but it's instead it's give more, but it just mark 1,000 at mapped region, and the other unmapped region will be keep as in use. So that's why it's a fucking magic things that malloc handle everything already. So this is mapped region. For example, we rent 8 bytes. Let's say if we rent 7 bytes, so this is gonna be 7 bytes, and this is gonna be the where that is not being used yet. So this is will be the break of the heap gonna be here. Okay, so let's move on. We have our mmap. If we want to use this in our tutorial, you should pay attention to the mmap system call. So yes, for this tutorial we're not gonna use mmap. We're just gonna use SBRK, NBRK as a whole, but not mmap. Well, for our modern mallocs, you will probably see how can I call this? Okay, it's that. Okay, let's queue this window, bro. Flash T0. Flash T1. We will try to do straight up malloc. Let's see. Yeah, we have to do it in file kind of. We have to run our files. I will demonstrate this real quick. cdcs.c. Let's do vman.c. Let's try some malloc. Okay, so we already have the library. So let's do initialize a integer pointer that equal to our malloc. That gotta be just an integer, right? So we're gonna see size out an integer here, sign p if you something, maybe 5. We're gonna print this. Maybe we just do this. I don't want to like have extra step when we try with s-trace. So just read this after and return 0. Alright, perfect. Is that a problem? Unexpected expressions. Okay, is there a problem here? Size of integer. Oh yeah, my bad, bro. What the hell is this? Okay, so let's try to compile our codes. That's O1 Malloc and try to run s-ray with our Malloc. So if you see here, okay, we have exec, brk, openapp. This is don't really need to care about this, but mainly we have brk, mmap, we're gonna have PRK. So this is what the modern Malloc is implementing, right? Gotta use mmap too, but mmap is fine. We're not gonna use mmap in this tutorial. Just give me a few seconds. I have to check some message here. I keep going. I was just kind of checking message. So mmap basically the same thing to Malloc. Loki, I can show you guys how we use Malloc. I know no I mean mmap, right? So let's go here. Let's go here quick. And yeah, I do not sure that if we need a library for this. Yes, we do. It is system mman.h. So let's have it here too. So it's mman. No, it's just system mman.h here. Let's delete all of this so that I have a pointer to map. Well, low-key, I'm not gonna return pointer 8. Hopefully, yes, it's gonna return an address. So, gotta be a pointer. Okay, the address. So the address is gonna be no, right? Try this. Alright. The address gonna be no. In that. No. Okay. And then the size. Low-key, we can have this size because it's gonna run up anyway. Gotta have pro. We can give it access to write and read at the same time. So you can then write and read, right, and apply. I'm low-key, I don't remember the flag. Maybe anonymous? Like anonymous? We remember. We have the flag. In math, it's anonymous. And do we have to map it with something else? Let's see if we do have something else to map it with. Failed, executable. Low-key, no. That's it enough. And this gonna be -0, and the offset gonna be 0. So let's try with this. Now we have the pointer. Can kind of assign this to 5, and we can print 5. P. Oh, my bad. P. It's gonna be the value of P because this is the address. Incompatible integer to pointer conversions assigning. That's pretty sure we have to map this into an integer, right? Oh, what happened? Oh yeah, my bad. Wait, hold on. Yeah, this is gonna be the value of this. Not sure. Sure. I feel stupid, bro. This look pretty. Let's try to compile it. If we have any error, hopefully no. Okay, pretty sure we have some error with the data conversions or this. Maybe this is enough. Yeah. Try to look at Google how people implement Nmap. It'd be great if we have an example here. I feel dumb right now. Example. Try AI give us the example. Let me see. Right, perfect. Oh. Alright. Alright, so cool. Cool. Okay. No, we don't need this. Like we can ask ChatGPT. Let's write a map. Simple. Example. Add this GL code. Be sure we have something wrong. Delete all this one. Okay, so it say that this is a perfect system call. Maybe I messed up something here. Oh yeah. Wait. Oh shit. This is the whole page. Yeah, I forgot. This is the whole page. Yeah. Bro, this is the whole page, which like thousands. Yeah, low key. We can do size off, just integer. It's gonna rhyme up anyway, but yeah, we have p0 equal to 5, and you know we can just print p0 here. Maybe no, but it would be great if you have an example right here. Yeah, I forgot. We don't need pointers here. So let's do gcc.so. And I'll see. I screen it. Alright, 2 error. Funny. This is funny though. What is wrong here? Seems pretty straightforward for me. Time p5. Yeah, maybe we need to unmap it, but I don't think it is necessary. Then Why we have error here? 696, like here. Jesus. Oh my gosh, I miss a flag? Nah, I'm stupid as fuck. Whatever, bro. How can I know? Like, how can I know, bro? Yeah. So we need to map this with privates, and now it's gonna work. Gosh, that me. See. Okay. Whatever. That's why we don't want to use a map in this tutorial. It sucked for me. I don't want to use it. Alright, so that is the demonstration. Now let's go here. Let's move on, guys. My bad. I waste your time. You will play. Yeah, we don't care about nmap, so don't worry. This is the implementation. So let's try with SB Arcade. This is what I've been talking about, so we can have an idea about what I'm talking about. So here, just look at the codes. This is a really simple, basic, and stupid Malloc functions that we initialize a void pointer, map it with the current location of the process break, and then we're trying to increment the size of the heap regions by the size of bytes. If it's failed, we're gonna return null, or we're gonna return pointer. Let's code this up. I will make a directory called maybe my library mallocs, maybe, and let's go to that directory. I will organize the code after we finish this. Not for now, but let's call this is malloc.c. No, we shouldn't. We just call this man.c here, and let's go to it. So we want to have let's go here to brk, what library we need. So we need uni standard.h. So let's try and include that uni standard.h. Perfect. So I'm gonna have our main functions right here. It's gonna return 0, leave it like that. A malloc functions that return a void pointer, right? Let's call this mallocs. We're gonna pass in pretty sure it is the size of the bytes, right? The size, and we're gonna initialize our p pointer with our p pointer with brk0. brk0, yeah. No, it's sbrk actually. Yeah, and then try to expand it. So if sbrk of a size is equal to void of star of -1. This is just indicate that it is fail. Like basically it is null, but this is the convention, so just follow it. No questions about it. So it's fail, just return null, right? And if it's good, I'll just return the pointer. Then we can try to call our malloc function here. Let's try it. Let's do integer p equal to malloc, maybe size of integer, right? Alright, so let's try to compile this. GCC NFC /layout. Oh yeah, I forgot, we can do trace.layout. Okay, so y'all can see we have our BRK right here, which is good. This indicates that our malloc it's working, but you know, currently we don't have anything working in our malloc. We just basically expand it. But yeah, we can try to, you know, write something in here. Maybe we can try that. P equal to 5 and then enough of a digit of P. Yeah. There's the address. Okay. Let's try to compile it. Oh yeah, we get error. What happened? Missing standard IO. Okay. Names our prints from bro. Is this from standard IO? Maybe I can just try to include that. Here's standard IO. Okay. Let's try it. See, let's try to run output. So here, y'all can see we have our own malloc. Like it's pretty fast, right? But no, it is not what you think. It is not what you think. It's not what you think at all. It's not that easy. Don't be happy, alright? So the thing is that we successfully expand our heap for size, right? We expand our heap by size, then we write 5 into the heap, and then we print it, right? But the thing is that we can free it, right? We don't have our free function yet, right? Because this malloc is our malloc. It is not the functions malloc. You can see that I didn't include the library from the malloc, so we're just using our own. So this malloc, we just doesn't have anything yet. We can't free it. What frees that our program actually free the memory for us every single time that previously you see a function say exact VE in our strace program. So it's basically the program refreshes everything, memory, everything is refreshed, so it's make sure the heap is clean. So which means that the computer, the operating system is the kernel doing everything for us. This is fine. If you forgot to free the memory and the program ends, well, it's probably fine. But if in the runtime, if your program running, you're using memory, keep and using it, you don't free your memory when you're not using it, it's gonna lead to the memory leak. It's gonna fuck up your program so bad, and that's why we had to implement free. And in order to implement free, there's a problem is that, you know, how we gonna keep track of all of the data, all of the like the memory that we had borrowed from our kernel. Bro, the problem comes. There's a bunch of problems that we're gonna go over this video. So let's keep going. Let's see. Alright, so here the author also say we represent a first attempt to code a Malloc function, but we failed to fulfill all the requirements. We can free it. Later on, we can reallocate it because we don't have any idea about where the current memory points to. And we kind of have we do have to improve our Malloc later on. So what do we need? See here. If we consider the program, I'm not going to read this, you can read this on your own if you want to, but basically is that we need a struct to store all of the metadata for our data. Yeah, which means that we need the metadata for our data. So we need a struct. This struct gonna store the next pointer to the next struct here to the next struct here. We also gonna store the size, which means the size of the data that this metadata represents, and we're gonna have a flag to indicate that if this data is currently being used or not. So of course this block is information before the pointer returned by Malloc. It's have to be before it's paused because it's the metadata is describing our data, right? Okay, so yeah, let's create a struct. Okay, we can have it here. Yeah, let's create it. Type that of our struct. It's gonna be named at x block. Gonna be t block. This is gonna be a pointer, right? Right. So here, let's have a struct. This struct gonna name s block, and it's gonna contain. First, it's gonna contain the size. Okay. Do we need a semicolon? I don't remember. Yeah, we do need semicolons. The next gonna be the t block, which is the pointer to the net metadata. Say next. Okay, now we have our flag, which is gonna be an integer indicating 1 or 0 for use or not being used. And yeah, we need a semicolon here. And for our t block, need to initialize this, pretty sure. Yeah, it's look good. Good though. So now we have our metadata. This is good. So let's implement our mouse. I have a notice thing to say here. You can probably read this proof your own, but basically we have to round the bytes that we are borrowing. How can I explain it? Let's imagine if you're borrowing just 7 bytes for an array containing or a string that having 7 characters for each, because each character is represent for 1 byte, but actually the kernel itself, it is smart and it's know how to run off the malloc functions really know how to run up the bytes that you are borrowing. For example, if you're borrowing 7 bytes, it's gonna run up to 8. If you are borrowing 10, it's gonna run up to 12. Why is that? Because later on, if you ever free the memory and reusing it, it's make sure that it's fit the conventions that you can use it to basically store any data type, including float, double, integer, char, right? If the malloc just allocate like directly precise 7 char, and later on you try to fit like 2 integer into that, it's gonna fuck up your program so bad. So that's why we need line 4 here. Yeah, we can define this here. You can try with this, try to plug in any number. It's gonna round up to a multiply by 4 that is higher than or equal to x, which means that if you plug in 4, it's gonna round up to 4, right? If you plug in 8, it's gonna be 8. But if you plug in 7, it's gonna be 8. If you plug in 6, it's gonna be 8. If you plug in 10, it's gonna be 12. If you plug in 12, it's gonna be the same as 12. So try with this. We're gonna have defines. Alright, so aligns or shit, I thought about x. Oh my gosh, this is so bad. I'm just gonna copy it. Just copy this. Alright, cool. Alright, cool. This is the bitwise. If you don't know what this is, just basically multiply by or divide by. Alright, so final chunk is the so this function is for when we are doing a malloc the second time or the third time after we free a memory. Basically what it's gonna do is that I'm gonna draw it here. So if you have a sequence of memory here, let's say here I'm gonna mark 0 as user and 1 at free memory. So if you're using, if all of this being used, right, and later on if you free this, so it's gonna now be free. So when you're doing another malloc, well, actually what malloc do is it is not creating a new space for you, but it's gonna check if it can reuse some of the memory that it's have enough space, right? It's gonna have to satisfy some um, requirements, of course. Yeah, and yes, if it's satisfied, Malloc gonna smartly use this. So that's why we need a find block function. So it's gonna find what memory is usable. So we can see here we have a find block, pass in the last, the size, and create a new base. File B, and it is not free and it is not um, like have more memory more than size. You can we're gonna move on, right? Else we're gonna return B. Yes, just simple as that. You can see that. Well, okay, I'll try to explain this. So for the find block functions, I'm gonna pass in the last drop, which is the metadata, and then it's gonna go over and over the next metadata. So just oh shit, handsome as fuck. Okay, so this is I hide kind of high, but just keep in mind that we have some metadata here that you know we will use this to keep in track of the next data that is point to, and later on we use to free memory and reallocate memory. So basically the last is imagine that is this one. Um, and the size is that, for example, if we using another new Malloc. Oh my god, my handwriting is so bad. This this Malloc gonna be something maybe maybe 5, right? So it's no 5 is stupid as fuck. Maybe 12. Okay, let's try 12. So it's gonna start with the base. The base is basically at the begin. Base is we're gonna set base is to null. E gonna set we're gonna set base to null at the beginning of our program. But if base is not null, which means that we already have something, we already have existed malloc, so we probably want to find proof the old like the old malloc memory, heap memory, right? So that's why we have a base here. So it is not null, right? And um, it is not free, like while it is still not null, and if it is not free, and if the size of it is not higher than size, then it's just gonna keep um, moving and moving to find the new chunks, like to find the next chunk if to just that satisfy what we want. We just go keep finding the chunk that we want. Okay, so if you don't understand anything, just feel free to comment. But I hopefully you understand. So we can lucky have our find block here because later on we're gonna implement it to our malloc. So that's why we need our find block to be here first. So malloc is gonna return a T block post, gonna find block. We can pass in a T block address last and a size T of sides. We're gonna create a new T block. B go to base. We're gonna have base here. T block base equal to null here. Um, base. So if base if no while base and not is not free and base of sides is higher than or equal than size we need, we're just gonna keep move our last to the next one be do we have to like move it here? Um Wait, my music gone. Wait, I forgot this one. The last gonna be B. They have a B. B is already the next one. B is the pointer. B is the pointer to the metadata. Last metadata. And then B gonna be point to the next B. This is like a linked list. Okay. Okay, this is have to be free, bro. Why is it flag? Like, okay. I just used the music, bro. I need the music. Repeat this. Alright. Let's go back to our mood. Let's go. Yes, sir. Send key. Yeah. So as I mentioned, sometime we do have a fitting chunks because the data we require it's actually fit the chunk that we already have that is currently free. But what if the chunk that we want is not satisfied in the remaining chunks? So we might need to create a new one here with a size, the bigger size that we want, right? That's why here we want understand heap functions and a define blocks size of here. This is a constant of size of struct. Understand? Okay, so I will go over and explain this for y'all. So the stand function could take in the last, which is the last T block, pretty sure here, the last T block here, before we stand this one, the size we want. Okay, we're gonna get the last heap address. So if sbrk blocks plus block size is null, return null, we extend this by a block size here because we actually need a space for our struct here, for our metadata and the actual data here. So that's why we need this block size, the size of our sblock struct plus s, right? And then I'm gonna set size to s and set the next pointer of this to null because it's currently not pointing to anything. So if last exists, no, last is pretty sure it's this one. Last gonna point to next. So which means that the last currently point to, which is referred to the last metadata. So now in this struct, its next attribute gonna point to the new chunks that we just created, and then yeah, basically that free is 0. Yeah, free 0 because we're gonna use it, the malloc. But yeah, so let's code this shit up. 2 blocks. Expand block. That's how we called it. Expand heap. Alright, bro. Whatever. It's gonna take in the T block. Take in the T block last and the size T of S. So what we're gonna do, create our T block B. So we're gonna have B equal to our sbrk. I just expand it. If sbrk of our define this here. Let's define this. Okay, we don't have block here, so we define here block size. Maybe size of our structure as well. Right. Yeah, perfect. Right, so we have our side block here. So let's have block size plus s is equal to, if it is assume that is a full treasury, and then gonna be next is gonna be null, and the size gonna be s, and let's see, say if alas next, if last exists, we have our last slash next will be point to b. We return the, oh yeah, we have to mark the current metadata as user. Oh, we have an error. SBRK of block size plus s is equal to SBRK of block size plus s equal to void edit ones. Probably have some error here. Do we need this? Do we need a semicolons? Do we need a semicolons after while we see? We tap on frame.
Ông làm xong để một khi nào xong ông nói với nhau để
That's it, guys. Alright, I'm thinking good for now. Just move on. Yeah, so we had our expand heap functions. Just keep going. Explaining blocks. Okay, so this is what I mentioned earlier. because here we always run up our stuff. That's why we always have some unused space in our data, and therefore we can split it and have another free chunk here. We can create a new chunk in here, right? So that's it. And one more thing here is that, well, for now, if we want to get the pointer here, which is the pointer to our data, we actually have to do b plus size of, right? Let's say this is size of our s block, or our no, we can do b plus our block size. Right. And we also kind of need to, you know, deconstruct this as a pointer or something like that. It's really annoying. Instead, we can use this char data once, so it's kind of smart that the struct here, this is the, oh shit, I just messed up, shit. So, bro, how to change this out? So, this is the real struct we want, but char, why we have char data 1 here, it's basically this is a trick that we're gonna get the pointer. So now if we return data 1, it's gonna be right away the pointer to the data. We don't like need to do this anymore. You can see it here. Yeah, I don't know, but just we just add that to our select char data 1. We can do 0 though, because an empty array is gonna be nothing, and C gonna treat it as an empty array. And we can now define our block size as 12 because we have our size. This or this gonna be round up to 12. But I mean, we can, because we don't want this, because if we consider the data, it's gonna be like more than 12, right? So that's why we want to have this as 12. And this, yeah. And here is the split block functions. Pass in the current metadata. Basically, we pass in the current chunk. It's gonna create a new metadata. The new one gonna be point at b, right? So it's gonna be from here plus s. This is s, which is the size. So we're gonna have the next one. So I'm gonna try it here so it's easier. So if we have, let's say this is the previous chunk and we want to split it, right? So this is the size that we are currently using. It just here, like 50% of it. So we're gonna create a new metadata right here by doing the pointer here, which is b data plus the size here plus s. So now we get the pointer, the metadata locations. Its size gonna easily be the total chunks, right? We gotta subtract. But this total gonna be yeah, the current size of the meta, this chunk like the old chunk, which is going to be the current size of the whole chunk. Gonna subtract with the metadata. Let's call this at nt, and we're gonna subtract it with the s that we use it, right? So now we're gonna have this is the size of, and we're gonna mark this into our new size, right? And the next would be b next, everything like that, kind of easy. Mark, and important things, we mark that as 1, which is unused, because this is currently the free space, okay? And then new gonna be size is now s. It's not size anymore, but it's just s, right? And b next is now new, not this one, but this one. So let's code this up. T blocked, split, blocked, gonna tag in, current B, size T of S. Yeah, let's split it like that. Yeah, we need this one because we just pass in. That's what? Now let's create a new block, new, here, and our new gonna be is that new? Oh yeah, the new here, new metadata, gonna be b data plus s, b data plus s. New size gonna equal to size. We have size yet. I do not know if we have size yet. Yeah, which is the current b size. Subtract for the metadata, which is the block size, and s. New 3 equal to 1, so just unused. And yeah, here new. Yeah, new next gonna be the old next of the old b. Next. And then b size, set new b size. B side now it just says and b is now here. Alright, pretty sure you guys understand, it's pretty easy. And yeah, we have this as no. Oh yeah, there's a void pointer like that. White version as well. Okay. Let's move on. Okay, so now here is the full Malloc implementations. It's gonna go over the code a little bit. Right. P last. So this is the real Malloc functions here. We just pass in the byte that we want, and it's gonna like smartly do everything in here. So we have the size here. We're gonna round it here, right? A base, which means this is not the first time that we allocating heap memory. So we had to find a blocked. Last gonna equal to the base, and we just start to find it. Pass in the address of the pointer. Start from here. So we'll just see if we can split this. So this one check if we can split this by, we check if size subtract for s is still higher than a chunk. Like if we try, this is the chunk we try to fit in. If b size subtract for s, which is the unused space, is higher than this, which means that the unused space can have space for us to create a new, a new chunk. So we're gonna split it, set that into use it. If not fit, we just try to extend our heap. If it is the first time, then we're just gonna extend the heap, right? So yeah, just implement the codes. It's not that hard. So let's fix this Malloc. Now it's gonna become a better Malloc than our first Malloc, right? C blocks, create B last. It's gonna be size T and one round of that once. Size, right? Yes. So if base is not null, set the last to the base and try to split it if we can't, right? Then I have if b or slice is subtract s is higher or equal to our block size plus 4. Yeah. Let's create that with this. Gonna try to split our blocks. Split the current B with the sides of S, just like that. And we're gonna free the after. Gonna free that. It's mean that we have used it. Okay, do I mess up anything here? Yes, I do. Okay, else we have this case here. Is not fit. I'm gonna have the gonna extend heap, right? Extend the heap. Last. Extend the last heap for S. Yeah, that's gonna portion. We already tried to see the base. Yeah, extend from last. If this or return null. And else here, if this is false, if this is the first time, then we just extend it right away from our base. Oh yeah, we're gonna extend from nowhere with the size of S. Oh yeah, side of S because we round it up as S. Okay. If it's base gonna be B, yeah. So if B is fail, we're gonna return null. Else we're gonna return B. Oh, I mean, yes, we're gonna return B, but we're gonna have our B data, right? Now base is equal to b. Yes. Right. Cool. Now let's implement this tree. It's gonna be really quick since we already have our full working malloc functions here. It's quite straightforward. 0 or 8 bytes in the blocks. If you don't know what calloc is, it's just basically like malloc, but we initialize every single byte within the memory that we borrow as 0. That's it. So here, create a new malloc, right? And having a loop over writes everything to 0. But well, I personally think this is kind of stupid. No, it's not stupid though. Kind of rude for saying that, but it's kind of like not having a proper, like a high readability for a beginner like me. It's disgusting for me to look at these codes. Really, like honestly, bro. Who the fuck write these codes? Let's have this void function here. Journal calls. Calls is kind of different when you want to pass in a number, right? The number, the size. So if the number could be integer, cd, Verda, size c, s. Just create a new pointer. Size c pointer. Yeah. So assign this new to calloc. Size c of. So it's going to be number times s, and having a loop of size t of I equal to 0, and I going to be smaller than the total size t total, maybe per time s, will be total going to be multiplied by first, and is yes total time for 5 plus nil of I going to be 0, and return them. Personally think this is better. Just basically mean we loop over every single time. We're gonna, for each size t, gonna write the bytes as 0. The reason we have time for he is because notice that the pointer news having a type s, the metadata of a byte. So that's why we need to time for he, because I here I is this gonna loop over plus 4 every single time. So that's why number times s. Maybe I can ask ChatGPT if this is correct. I just don't want to mess up and if this is correct. Okay, this is incorrect. Glad that I checked this. Yes, I tried. See it goes. What the fuck is this? Yeah, pointer gonna be char. This is gonna be char though. Yeah, low-key this should be char. But the other than that should be size is not 0 or number is higher than number is higher than size of max. What is this, bro? The fuck? Loki don't really need that. Let's just implement what he say, bro. I'm gonna explain. Just have side C. S4 of total and right here. And this, okay. Line this and then on 4. Okay. Okay, so if sign total, it's our lines of number size and multiply by 4 divided over I equal to 0 plus 1 grand total plus 5 there as okay, so I'm gonna explain this. So we create the new pointer nil total I. I'm gonna borrow first, gonna do malloc, and then if the malloc success, we're gonna round up, of course. Calculate the total bytes we want, and then we want to multiply it by 4. Why is that happening? It is because the current size of the nil is the data type. It is size t, so each write is gonna be a size t, which is multiplied by 4 because you guys already know size of size t is 4, so that's why we leave that. And then yeah, after single time we loop over that, we just want to write the whole sequence of bytes into 0. Now we're gonna implement free. Okay, so let's implement free. They have fusion. How long is the video already? Okay, 1.2 hours. So fragmentation basically means fragmentation basically means here, if I have a sequence of data here, right? if I use this, all of this, later on, if I'm not using this anymore, and not using this anymore, if I want a program or something that want to use this spot that is not enough, having enough sites, well, instead we can merge this, right? So this can now, the whole space become an empty chunk instead, right? So that's what data fragmentations come like. You know, it is we cannot use that, instead we can like that. So we can use the fusions, which is here, that we will fuse, merge the previous chunk with the current chunk that we want to free, but it is empty, also empty, right? Which means that if we free this, and then we free this, and this gonna check if, you know, the chunks nearby is free or not. If yes, it's gonna merge the whole things together. So let's implement fusions. Yeah, let's go over the code first. We're gonna pass in b. B gonna check if next exists, and it is free. So if it is free, the size of it gonna be increased by the block size, which is the metadata plus the size of the next chunk. And now this next gonna point to where the next should be, and if the next exists, right? That chunk previous gonna be point to B, which is the current chunks, if you understand. So we have to add this prep. So here, set that. Yeah, so we do have to kind of change a little bit. And I mean, I think we can still use T-block Loki. Let's use splitters. Yes, let's implement this fusion. What fusion? Return the T-block. Am I spelling it right? Oh. Alright, merge current box here. So if the next is exists, and the what your next is currently free. B size is gonna be equal to current B size. And we got plus something. Yeah, which we can do plus equal instead. The block size. B dot next. B next size. And we can do B next is now equal to what? The B next previous point 2. So if B next exists, we're gonna have our B next previous gonna point to B, right? Yeah, perfect. And then after this, just return B. Perfect. Oh, it's gonna hurt. I need some water though, a bit. One sec. Alright, let's keep going. Let's find the right chunks. Okay, so the problem is that when we are trying to free a memory from the heap, what we do is we're gonna pass in the pointer of the memory, right? So, for example, let's say here, if we do integer p is equal to malloc.5 something 8, later on the free this pointer, right? We free the same pointer, so we wanna have to ensure that we are freeing the correct pointer. So how do we know this pointer is from the heap, from the malloc, but not any random pointer that pointing to any address that is on a stack memory, right? So that's the problem. So the author here, so we have several ways to validate the input pointer by initializing it with the pointer. So basically we assigning the pointer with the data. Let me just go up here. Yeah. So here, this is what we have. Data, and then a void pointer. So this pointer, we want is that the pointer gonna be equal to the data, which is the pointer to the data space. And we need a get block functions. Let's see what we do right here. Alright, that was strokes, that's fine. Get block from address. This get block just basically make the pointer, it's gonna assume that we are the current it's gonna assume that we are freeing a valid pointer from the malloc, so it's gonna like go back by block size. So this pointer assume that we are pointing to the correct data, so it's gonna go back. Gonna go back to the metadata right here, and we're gonna check. We have the valid data. We're gonna check if this get block pointer, get a pointer from it, and see if it is equal to what we are checking. Like, this is what being stored in metadata. This is what we pass into the free. So yeah, we want to have this get block and valid address too. We have this here, right? So have it C block, get block, right? But there's a P R M and current is that we cannot do pointer arithmetic with a void, so we cast it into char, so it's gonna be more precise with its byte. It's gonna be char, like its char will be 1 byte. So then we're gonna return, return a p equal to temperature. So gonna minus by block size, and do not need that. Oh yeah, let's go to block size, and we're gonna have our two block valid address passed in the address, check if base, return. So if base, which means it's not the first sign, then we can check, right? This is not the first sign. I'll check if P, yeah, P is higher than base and P is smaller than S. Yeah, we can do SBRK0 instead. Okay, so that is 0. Okay. So this is checking if the thing we are freeing is like inside, like in the middle of the sequence. Because if it is out here, we're gonna do extra thing is that if we free this, we can delete this from, like, completely free this, or if there's nothing behind this, right? We free this one, we can now set the base into even null, because basically there's nothing else. This is the only malloc that we borrow, right? So we're just gonna return if D is equal to our get block, and for this get block in D2 and 100. Yeah, perfect. Yeah, any error here? We'll look at, yeah, we do. Do we? Get blocks. Yeah. Let's go to our free functions. Let's move on. After the free, we can test with our blocks. So for the free, we're gonna accept the pointer P, gonna check if the pointer is valid, it's gonna get the block, set it to unused, right? And we'll check if the previous or the previous is free or not. It's gonna fusions, as I mentioned. If the next one, which is the one on the right, is fusions, is empty, it exists. I mean, it's gonna try to fusion too, right? But if the right one doesn't exist, which means that it's on the rear, like at the end already, that block we want to free, so it's gonna remove that from the heap totally. Yeah. So it's gonna happen to say what we take in our part B. Okay, let's make this C copy if Alex address of P, right? P gonna be equal to gonna get block of P, right? Set it into free, right? Check if the previous is free, right? Oh yeah, we have to check if it exists, then we can check if it's free. Now we can do B equal to fusions with the previous and check if B next exists. If B next does exist, we try to fusion this too. Oh, why is the fusions down here? I have to move that up. Oh shit. Malloc. Okay, cool. Gonna fusion enough. 2, right? Fusion B? Oh yeah, because B is on the left, so yeah. And else we're gonna free it completely. So here it is, right? With B previous, and next gonna be no, right? Else set the base into null too, because previous doesn't exist mean that is the only mallocs in the program, and we're gonna return, we're gonna do brk of B, which is set this brk to the start point, which is 2 base. So yeah, looks pretty good. Now we can try this low-key. And then we're gonna then free the pointer. Let's do GCC that's code, and when I see yeah, some error first. We have an error in our valid address functions. Let's go back and check. Let's go back to the box address. Return. Get one. Yeah. We're not returning a T block, right? So here, get address. Yeah, we return integer, so that's why. Because it is here, we just return, you know, one or 0, just 0 false. And let's do GCC, that's O. And then let's do the other error we have is T block right here. Here, go to the business. Split block. Is there anything wrong here? Split blocks. I don't think there's anything wrong. I don't think if there's anything wrong. Oh, this is voids because we do not return anything. Just like that, so it looks why. Yeah. Okay, for incompatible type of char. Kinda, I get it. This is char, so it's gonna conflict because this is the 2 block of meal. This should get this error. We have AI debug brush. Oh, find what does return. The fuck is this about? Oh my goodness. Does not return in OPAD. Now return 0 here. Centralize B. Let's check with their codes. Check this. Size. Oh, we have to find the first block in order to, flip this. Find blocks. This will be blocks. Yes. Right. Yes, the address of glass. Right. Is that? Could be a spam, but let's change everything to a spam. Spam. Probably the spam. Oh gosh. I think it is fine, okay. No. Oh shit, what the fuck? Oh shit. Yo. Where the fuck is my file? Yo. Alright bro, what the fuck? Oh my gosh, just disappeared, bro. Alright, this is trash. The fuck? I have to fix. No, I hate this. Yeah. Let's go over the error again. Okay. Ignore this. Ignore this. Find box should return B. What address? User answer. Okay, fix that. Yes, bit. Type. Hi. So yeah, this suggest error. Oh yeah, because we changed it already. Yeah, makes sense. Now we have many of this, so this can't be 12 anymore. Instead, it's going to be the size of this subtract by the size of char. Okay, makes sense. It's incorrect. T block, cast it into char. Subtract for block size. Yeah, valid. Valid. Oh. The type gonna be T block. That's the type before it cast it into. It cast it into our char. Let's look at here. Casting it into char, right? Char. And P subtract for our block size. Yeah, I miss a semicolons at the end. This is wrong type. Let's go to split functions. This is wrong type because this is, you know, char, but this is T block. So we can't really like map that. Sorry. I can't speak much because my fucking roommate is sleeping. I mean, I love him, but just chill. Yeah, I have T block. Cast this into the T block. Alright, it's pretty cool. That's the whole thing. That was good. If Neil point to next want to do this searching them. They're gonna be lines with size as next. Okay, different. Here, next. This is a really bad tutorial on the website. Add this. The point can be the data. The point can be the data. And the cube is gonna be the last. Okay. Yeah, valid. Yeah. Oh, here. Have to find it. That here. Usually find block glass. Glass. Yeah. So there's a glass for that. This one. Bro, just follow the tutorial, bro. Look, yeah, I just replaced all of this, bro. Side max this one. I'll just keep that. I'll try to. Let's try to compile code to see if it's working. Soon if I get here when no free block found.
What's the problem, bro? If B and oh shit, bro. That's equal to base if base. Find block if base. Sign here. Split block else. Missing the return here. Makes sense. Just return that over here. Try to go here, back here. Sure, Malloc. Yeah, return out here, not here. My bad. What is this, bro? If E and what? This guy covered this. Keep missing? What the fuck, bro? Oh my gosh. This missing what? Oh. Yeah, I did duplicate, bro. What the hell? Cash. B next. 1B. Okay. New previous will be new previous is B. I think calloc is good. Don't give a fuck. This is good. This looks good. So, let's try it. Names. Let's see. Exactly. Alright, bro. How about this? If it's wood. So probably not that problem. We're still suggesting. Find blocks. Check if B and split block is gonna free, else is gonna stamp things and return data. This happens when B is equal to null. Else motherfucker snoring stop, bro. Shit. Monkey. This thing for a stand. I mean, like, focus on ChatGPT. Okay. This is last. Return null, and we do not sell spaces B. Just kind of let's use what you did. Alright, cool, good. Yeah, we're gonna free it right here. Oh, we have a duplicate here. Shame to. Delete that. Give this value to set this. Oh gosh. So let's try to test it before doing. Alright, so what? Oh my gosh. Let's have a look at the flow again. So the assigned sides have B round sides if base exists, which is not the first Malloc. We're gonna have last equal to base. Last equal to current base. Gonna find block from last to s. Yeah, makes sense. If block access is gonna check if the remaining sides can be fit in to be split, and it's gonna split in 3. Let it be as unused. If it's gonna split, it's just gonna extend the heat because it's on the rear, like at the last point. So we're gonna extend it, right? Alright, at the end I'm just gonna return the pointer to B if base is not in, which is in the first time that we're gonna extend the heat from the falls. This we're gonna extend at least from last resistance. Okay, makes sense. Set base to B. Alright, so yeah, I hope you guys understand this tutorial speed off, and it's been a while, so it's be late. So yeah, we have our mountain free and calloc picture class can't work. Maybe we can try. Let's try with signature. This once and set up integer. Maybe bring up digit B and 2 digits dash. So let's see and once C. So yeah, sprint 0. Okay, it's perfect. So yeah, it was working just fine. So yeah, I hope you guys enjoyed this video. Please leave a like, comments below if you guys have any questions or we can discuss something. It's really late, so bye bye. See you on the next video.